My name's Simon Hackett, and as a brief introduction, I had a significant career in the internet industry, providing broadband services and, amongst other things, created the world's first internet toaster. A long story and not perhaps one for today. After that, I moved into the energy storage sector and became involved in particular with Redflow. And Redflow make what I think is a very interesting device that I'll tell you a little bit about today. And I have become the largest investor in Redflow. I was on the board for a while, even ran the company for a while. But these days I'm back to what I prefer to do, which is to be in the lab working on technology, on the technical aspects of how the battery works. So today I'm going to tell you about three things broadly, to give you a bit of an introduction to what the Redflow battery is, for those of you that haven't come across it in the past. And it is indeed a flow battery. It's one of those rare examples of a not lithium battery that's doing interesting things in the world. I want to talk about one aspect. I'll tell you a little bit about it and about some deployments of it. I want to tell you a bit about a thing called standby power system mode, which is quite an interesting and innovative use of the fact that this battery is a little bit more than just a dumb box of chemicals. And then talk about how we're taking the Redflow flow battery technology, modular battery storage devices, and starting to deploy them at the bottom edges of grid scale and having fun working out how to scale the technology up in various ways. There are some significant challenges with conventional batteries, and I guess the thing about them is, as we've heard from our presenters so far, lithium batteries are incredibly popular, and for the right reasons. The economics have become extremely competitive. They're highly energy dense. They're really the only rational choice for transport in a vehicle. But there are always other places and other uses for batteries and other locations where the downsides of those batteries can actually mean that you lead to looking at other choices, either instead of lithium or in a hybrid with it. So just briefly, you're aware of these things, I'm sure, but lithium batteries have some challenges about what happens at end of life, recycling and disposal. They, in common with a lot of battery types, lose capacity as you use them. So the longer you work a lithium battery, and importantly, the longer you work it in deep cycles, the greater the extent you reduce the amount of energy that it stores. So some of that economics gets lost over time as the storage capacity of the device diminishes with use, and again, especially with heavy use and deep discharge use. And as a result, a significant chunk of capacity in a lithium battery array has to be reserved to protect against that degradation. It mitigates against some of the economic nature of the batteries. Obviously, they're still getting cheaper at a huge rate. There's some other issues. A lot of batteries other than flow batteries have issues with reduced life in high temperature, which means that you may have to temperature control, even perhaps air condition some battery rooms in hot environments to avoid high temperature degrading the life of the battery. That's something flow batteries don't suffer from. And the other one that's the classic thing about lithium batteries, they are very energy dense, and it means when they do actually short out, or when there is a problem, that problem expresses itself typically as fire, and in particular as an exothermic chemical reaction. That means that when they catch fire, they properly catch fire. It's very common and accurate to say that lithium batteries are continuing to get safer and safer with time, and they absolutely are. But nonetheless, the fires do happen, and there are some environments where you aren't capable of tolerating that as a choice for your battery facility. An interesting example of that happened literally just 2 weeks ago here in Australia, in Victoria, another state in Australia. On the 30th of July, a large Tesla-based megapack system, 300 megawatt system, caught one of the main battery modules in it, one of the main battery containers caught fire during commissioning testing. And as an impressive example of how hard it can be to put these fires out, it took 3 days to extinguish the fire and led to major air quality alerts across big chunks of Melbourne, because when these things do burn, the smoke involved is not something you really want to breathe in. So a big chunk of Melbourne literally was told to close their doors and not leave home for a while. Sadly, due to COVID, they weren't in a position to leave home anyway, but it's still a really good example of the fact that these things have some downsides that go with a high energy density. Net, they're still the thing that's going to win the majority war. in terms of what sort of storage gets deployed in the next few decades. But the message I want to give you and the thought I want to give you is that we're in an environment where the amount of energy storage demand in the world is just incredibly high and is going to be enormously high, as we've already heard this morning. And that means that for alternatives to lithium to win, lithium itself does not have to lose. There are plenty of places to deploy alternative energy storage mechanisms where those make more sense, or again, in hybrids in a lot of cases we see with lithium. So let's talk a little about what the Redflow product is. It's that thing you can see on the bottom right. For a sense of scale, that object is around about, to go back a step, typically flow batteries are very big objects. The largest flow batteries, a lot of the vanadium flow batteries are literally building size. Redflow was founded on the notion of producing the opposite, of trying to make the world's smallest production flow battery. So that device you see is about the size of a bar fridge. It's about 800 millimeters long, and it's really quite a compact device for a complete functional flow battery. If you have a look at the technology comparison chart on the left, the salient points about a flow battery are that the cost does wind up competitive, especially as we ramp volume up on this. We actually see ourselves chasing down the cost curve quite effectively. There's no material loss of output capacity with age with a flow battery. So as it continues to operate, you can expect to continue to get the full output capacity every cycle as it ages. Doesn't care about operating in hot environments. It'll run up to 50 Celsius without any degradation to its function. You can cycle them all the way from 100% full to completely empty every day. And in fact, the thing about a flow battery is while that cycle damages a lot of other batteries, that complete cycle all the way to full, all the way to empty is in fact exactly the way to advantage the life of a flow battery. It's what they like. It's what they like using, what they like doing. And they've got a very low risk of thermal runaway and fire. Indeed, the electrolyte inside these batteries, zinc bromine electrolyte, bromine is actually a fire retardant. One of the running jokes we have at Redflow is that if you had a lithium fire, one of the things you could do to put it out is pour our electrolyte on top of it. It would actually act as a fire retardant. These are very small units, as I said, but the idea is that when you want to build large energy storage systems, you just put lots of them together in the same way that the lithium industry does. And you get a whole lot of advantage out of that in terms of high availability. Also, they're made of recyclable plastic. The zinc bromine electrolyte is made of very easily obtained objects. That electrolyte is recyclable at the end of life. The plastic's recyclable. So there's a lot of good stories in there. Now, I'll just move to the next slide, if I can manage to make this behave. There we go. That's another look at the actual battery. And so it isn't simply a box of chemicals. If you look at what you're seeing on the screen there, you've got two electrolyte tanks in the middle of the slide. There's two pumps on the right. There's an electronic control box on the top right. And the object on the top are the electrode stacks. That's where the magic happens in this beastie. And so the fluid is actually pumped through that electrode stack. This is a slide won't study in great detail, but when Daniel hands the slide packs out, you can have a look at it then. If you're into the chemical reactions involved, what this device does is actually a little interesting. It is in fact a zinc electroplating machine made of recyclable plastic. So what happens is when you want to charge this battery, when you are charging it with energy, the zinc that's in the fluid comes out of the fluid and is plated in very thin layers on top of a conductive plastic membrane. So the zinc is electroplated inside that stack. When it's time to pull energy out of the battery, and it acts just like an ordinary battery when you're using it, if you're discharging, what happens is that the zinc just goes back into solution in the process of that discharge. So by the time the battery is completely empty, all of the zinc has gone completely off of those plates again. And that's actually the secret to the long life of these devices, which is that when you completely discharge it, all the zinc comes off of the plates and you've got a new battery again. This is the next generation of battery we're working on. The previous slide, you saw the current production model. This is the version that's been in the wings for a while. It's currently in pre-release testing. We'll be starting to make this towards the end of this year. It's a version designed for high volume manufacture, designed for machine manufacture. The current battery to date has been relatively labor intensive to make. This battery only uses one stack instead of two. It stores exactly the same amount of energy. It produces the same performance, and it's actually slightly smaller. And the result is that a system you design with our battery today will work just as well with this one tomorrow. It's just that the battery will cost less money. They've been deployed in lots of places. Here are just a few pictures of some places we've stuck these batteries. This is again, in the state of Victoria in Australia. This is a large assembly of these batteries and a lot of solar in a childcare centre. There's 2 of these that were deployed. And this is a typical deployment for Redflow. These batteries are very well suited for commercial and industrial use. We do have them in homes, including my home, but they're really targeted at telecommunications, industrial and commercial deployments. And now, interestingly, we're starting to head towards grid scale ourselves. This is another example of a heartland deployment for these batteries. It's telecommunications. This is in New Zealand, a 50 kilowatt hour deployment with wind and solar and a generator on top of a mountaintop. It's been banging away for years up there. And the propensity of these batteries to support deep discharge and to be very happy to work in harsh environments is really what drives their use in telecommunications. This is another telecommunications deployment, more recent one. It's in the far northeast of Australia in Queensland in a place called the Daintree Rainforest, a very environmentally sensitive area. This is a deployment with 6 of our batteries, 60 kilowatt hours of storage. It's a diesel runtime reduction exercise, and putting the batteries in, allowing them to interact with their very deep cycling with the solar to maximize the time the diesel is off, has reduced the diesel consumption of this site by about 70%. Now coming to South Africa, this has been a place where Redflow has been deploying these batteries for years, and it's a very, very good place for us to put them because they don't mind operating in hot and harsh environments, and South Africa is no stranger to having hot and harsh environments. This is a mobile phone deployment being put in South Africa. There's a number of these that we're rolling out now. This is an interesting one because what you can see in that cabinet is that there's only one of these batteries sitting there. So this is a 10 kilowatt hour backup energy storage device, replacing the use of lead acid in this telecommunication tower. There's a couple of key things about this. It leverages a thing I'll talk about next, standby power system mode, to make it extremely energy efficient when it's waiting for the grid to fail, when it's on standby, waiting for its job to do. And its job is to keep the tower going if the grid does fail. The other thing about these batteries is there's quite a black market for lead acid and lithium batteries, especially in South Africa. There's no black market for these. It turns out that's for a couple of reasons. One is there's some anti-theft magic built into them. So if you steal them, they just stop working. And the other is that they're relatively heavy compared to a single lead acid battery or a single lithium module, about 250 kilograms. So it's hard to run away with it. And if you do run away with it, because it's unusual, it really doesn't have a market in terms of black market resale. So one of the definite benefits of this battery in this application is actually asset protection, in the sense that it's more likely that your asset is still going to be there. This is another one in South Africa. This is Bosco in Johannesburg. This site's been running for ages. It provides backup power and peak charge avoidance. So it does some arbitrage in order to avoid paying for power when it is the most expensive. When the power fails, this system keeps the factory running and lets them shut their manufacturing line down cleanly, rather than losing all the material in their production line when the grid fails, or if the grid fails. Next, I want to talk to you for a few minutes about that standby power system mode. This is quite an interesting mechanism. I mentioned, I think, that the battery is effectively an energy storage machine. It has, in a lot of ways, in terms of its use cycle, got more to do with pumped hydro. It's more like a pumped hydro box than it is like a battery, because it is a machine that stores energy. And so because it's a machine, you can do something really cool with it. You can charge the battery up completely to 100%. You can then put it to sleep in the same way you might put a laptop to sleep. And at that point, the pumps that run the battery are off. The electrolyte fluid drains back down into the tanks, leaving just the zinc on the plates, dry on the plates in the battery. And now, just like pumped hydro, you've stored energy and achieved the potential of discharging it. But now that battery can sit there, just like a generator, just like a standby generator, consuming no electricity, no self-discharge, no internal degradation. Nothing's happening at all. It's completely quiescent, just sitting there. When time does come to take the energy back out of it, if the grid fails in that telecommunications site you saw a photo of, then within 30 to 60 seconds, the battery can be fired up again. And that just involves inserting a very small amount of energy into the pumps. And that energy is actually stored in some ultra caps that sit inside the control box. So it's completely self-starting. If the grid fails, the battery starts itself up, just like a generator, fires up and can deliver that full 10 kilowatt hours back into the application. So what you get is something remarkably similar to a genset, except that it has no diesel in it. It has no diesel maintenance. No one can steal the diesel, doesn't use fossil anything. And it can sit there on standby for enormous periods of time, days, weeks, months, years, before you use the energy. So really quite an interesting use of the fact that it's a machine that stores energy, a little machine, miniaturized machine, rather than merely being a box of chemicals. And any box of chemicals, if it just sits there, there's always some self-degradation. There's self-discharge, there's long-term chemical degradation. It has to be, it's unavoidable. So this is quite an interesting approach. One of the things about the standby power system mode is it can be done, as you saw with that telco site, where the single battery or lots of batteries are just being a standby power system and nothing else. Alternatively, if you have a lot of our batteries, and this is actually a picture from our battery management system showing 14 batteries running on a site that I manage. And in this case, of the 14 batteries, you can see the bottom 8 of them are actually in standby mode. They're in that list saying they're in standby mode. And the top 6 of them are running normally as batteries, what we call run mode. And so what's going on here is you've got 60 kilowatt hours of operating energy that acts just like any other battery, and you can charge and discharge energy into that. And this is a site with solar on it. And if there's enough solar, the 6 batteries are enough to keep the site running overnight. That's lovely. When you've got bad weather, when you have a bad solar day or a few days in a row, the battery management system simply wakes up the standby batteries as required and in sequence in the size, in the number of units you require at each time, and deploys those like 8 little miniature gensets that fire up on demand to add more energy to get you through the night. And then the next day, hopefully there's a bit more sunshine and those batteries get recharged again and go back on standby ready for the next time. And the benefit here is that those batteries that are on standby, again, have got no self-discharge and no internal self-degradation, so that you get a lot more energy efficiency out of these machines by in fact turning the machines off. And you can have this sort of hybrid structure that you can see where some of them are on standby, some of them are running, and you can play with that configuration over time. You can modify that proportion. And the battery management system that I designed, as it happens, orchestrates all of that process. See if I can click the right button. There we go. Last thing I want to talk about is a thing that we call PodZ. Z for, as in Z for zinc. And these things obviously use zinc inside them. And one of the things we've done in the last several months is designed a modular way to start bringing our batteries up to grid scale, to start doing what you see most commonly these days with lithium container deployments. That little picture you see there is the first instantiation of what we've built in this modular way. We can build various sizes, but this has been a really good starting size. Each of those cubes that you see on the screen, the gray cubes, the dark gray cubes, has got 16 of our batteries in it. They're 10 kilowatt hours each, so that's 160 kilowatt hours in each of those boxes. And then the little vertical lighter colored boxes on the diagram are the electronics control box. And one of the things that you need to do when you go to grid scale is manage enormous amounts of energy, by definition, grid scale. And so to do that, you need to raise the voltage at which you're operating. Our batteries are 48 volt batteries. They were designed originally for telecommunications. 48 volts is exactly what you need for that. When you want to operate at grid scale, typically if you're running a DC coupled array, you actually want to run at something like 600 or 700 or 800 volts in order to reduce the current flow and the size of the cabling that runs between all of these containers. To do that, what we've done is deployed a really cool product that's relatively new that was actually purpose-built, designed for 48 volt flow batteries. It was very much something built for people like us. A company with a rather curious name of Trumpf Hüttinger, who are in Germany. They're a multi-billion-dollar industrial company. They make all sorts of things. They make all sorts of lasers and all sorts of interesting industrial machines, and they've moved into high energy efficiency power conversion technology. And the key they make is something rather magical. They make a bidirectional power conversion unit with the name of a DC 1010. It's a 10 kilowatt power conversion module that you can cluster. Each of those can bidirectionally convert between 48 volts DC and let's say 800 volts DC. So 16 to somewhere like 16 or a 20 to 1 ratio of energy conversion in terms of voltage. And when you step the voltage up by a factor of 20, you step the current down by a factor of 20. Same thing you do with a transformer in AC, but in DC, you need some pretty innovative electronics to do it efficiently. And these guys make that innovative electronics. And we've been working with them for quite some time on this. They also make AC modules that go with that system. So you can plug their AC modules into the same control cabinet in order to make this a natively three-phase AC cabinet instead. So you can connect all of these up using three-phase AC directly, or you can hook them all up with DC and use a third-party high-voltage DC inverter to connect it to the grid. Really, really nice system. So let me show you what that actually looks like, because that thing just looks like a diagram of something we imagined we were going to make. It turns out, and here's another diagram of how we hope to see it deployed. This is an example of what these arrays might look like set out on the ground if you were building a 20 megawatt hour system, which means about 2,000 of our batteries laid out in these modules. And it's just a matter, as you can see, of laying them out in rows and getting the job done. All pretty straightforward. What I was coming to, though, is that looks like a concept drawing that suggests we think it's a pretty neat idea, but we haven't quite worked out how to do this yet. It turns out we have worked out how to do this. And this is not a theoretical product for us, it's a real one. And here's a picture of one of these things just before we buttoned it up and put it on a ship to send it overseas. What you see here on the left is that cabinet, which has got the 16 batteries in it. And those batteries are 10 kilowatt hours each. There's 8 of them on this side, 8 of them on the other side to make the 16. You can see the orange wires here. That's bringing the power in to the 48 volt DC bus, which is that device in the middle of the electronics cabinet. And then, in fact, let me move you to the next slide because it labels a few more things like that. Those power conversion modules I mentioned are down at the bottom right. So there's 10 of them. They can move 10 kilowatts each. This is rated at 50 to 60 kilowatts of throughput, this particular overall device. And the thing that was a bit of a head spin even for me, even though I understand the numbers pretty well, is that what this does is takes you from 48 volts and 1,000 amps to 800 volts at only 60 amps. And that means if you look at the wires on the back of the wall, just to the right of the words 800 volt DC interface, those tiny little thin wires, they're carrying that energy out at 800 volts, ready to go out to the next cabinet along. So it's very impressive the extent to which raising the voltage and raising the voltage lowers the current. And that little interface behind the label, 800 volt DC interface there, that then connects onto the next cabinet and the next cabinet and the next cabinet. So this module is then a 160 kilowatt hour, 50 kilowatt module, and you just keep stacking them together. And the next thing about grid scale deployments for these sort of batteries is the question is, where do you do it? And we are working with people like Arena in Australia towards finding some suitable projects that we can use to deploy these in a hybrid with lithium batteries, because one of the benefits of flow batteries is they're very good at a thing called long-term storage. Long-term in the context of batteries means more than 4 hours. California in particular has got very into the notion of building long-term storage for shifting large amounts of energy around, not instead of using lithium for grid services, but as well as. And there's a real benefit in that hybrid notion of moving large amounts of energy back and forth, pumped hydro style with these things, while you simultaneously handle very short-term, very high energy requirements like grid stabilization with lithium arrays. That thing you saw is actually a module that got buttoned up and put in the ship, as I said, and it's going to America. Our first large deployment as Redflow is our largest one to date. It's small in grid scale, but for Redflow, it's a really large step forward. This is a deployment of 192 batteries, so just under 200 batteries, delivering 2 megawatt hours. And that deployment, and you can see it there with inside the green circle, is at a place, is at a company called Energia. They're located about 40 miles east of Los Angeles. And we are in the process of deploying this system right now. It'll be commissioned towards the end of this year. That 2 megawatt hour flow battery storage is attached not to solar or wind, but to a bioenergy facility. And this is a simple case of addressing the duck curve, the thing that one of our previous presenters has already pointed out, that you get peaks, 2 peaks during the day that don't match the presence of solar. And this 2 megawatt hours of storage is in fact going to be charged up during off-peak periods by the bioenergy plant, and then at 5 p.m. every afternoon, right when people in Los Angeles are starting to get home from work, that entire 2 megawatt hours will be deployed into the grid at 500 kilowatts. So it'll spend 4 hours throwing 500 kilowatts of energy into the grid when Anna Ergia get paid the most money for it, but also importantly, when the grid needs it the most. And that's the point, is that the need and the cost actually drive the right behavior here. So this is a really good start for Redflow in terms of bringing ourselves up into grid scale. And we see a lot of potential in California in particular, because California is really seeing the light about the merits, again, of hybridization of flow and lithium, long-term storage as the piece that the flow batteries do. And they're putting a lot of money and a lot of effort into that because they can see the merit. Somebody's having a chat. Maybe we can hit mute. Last slide. The thing I wanted to say about flow batteries in summary. Ooh, now, that noise is my doggy who's seen something out the window. Just let me have a quick word to her. Oh, she's happy. Okay, noise is everywhere. Let's get back to business here. Actually, let me have a quick word to my doggy. 20 seconds. There you go. It's getting dark here in Australia, and she's starting to see things in the window that aren't there. Thank you, darling. Right, now she's back to helping me. So here's the thing about grid scalable flow batteries. I see, and we believe at Redflow, that there's a substantial role for long duration storage using flow batteries, not instead of lithium, but in concert with it, in deliberate hybrid with it. And we are hopeful of building some projects that demonstrate that hybridization in Australia, because we think that would be a very good way to kind of prove the point. That standby power system mode that I mentioned, it's a very powerful part of this, because it means that your long duration storage can be as long as you like. You just charge all the batteries up, put them on standby, and deploy them at whatever time frame suits you. And meanwhile, they don't have any internal self-discharge, which is why, as I said earlier, it's really got a lot of commonality with the concept of pumped hydro. You get 100% depth of discharge, you don't get thermal runaway. This one isn't going to burn to the ground. Strong recycling story, capacity is retained with age. So overall, we think there's a really strong role for these batteries, and we're really just starting to hit our straps with them. And again, not instead of lithium, not a competition. It's the reality that there is so much demand for energy storage that we are about to see in the world, that there's going to be a place in the sun for all of us. And that's the last of my slides. Thank you for listening. And if there's, I don't know if there's time for questions, Daniel, or not, but there you go.
Thank you, Simon. Thank you for the nice presentation. And I have seen there are a lot of questions.
Oh, there are, aren't there? Wow. Yeah, I've just opened the chat window. Sorry, guys. I hadn't opened it while I was talking.
There are a lot in the chat box. I'd appreciate if you could respond some of those.
All right. So let me do that. Let me just step down some of those. Where's the...
on another point, Simon,
right.
Before you fly, when is your time to sleep? 1 hour, 2 hour, 3 hour?
I'm a busy man. Yeah. Like all of us, right? We tend to run the midnight oil a bit.
Okay.
So let me have a quick look at these questions. Is it only used for stationary storage? The answer is yes, because they're relatively they're more energy dense than lead acid, but much less energy dense than lithium. So it only makes sense in stationary storage. You wouldn't stick one of these in a vehicle. It just wouldn't be energy dense enough to be worthwhile. So they're a stationary storage device. So hence no direct application for being in the EV, but plenty of application for being in the charging station, right? For being the thing that is charged up to store energy in the charging station for the time when the electric vehicle arrives. So the stationary application is it. Any opportunities for management and maintenance of this energy storage system? Yes, there are. Because it's a machine, there is some maintenance involved, in the sense that there is some merit in at least an annual visit to make sure the machines are happy. We do think there is some merit in that, and we are starting to look at kind of rational models for that, both in terms of that sort of management, also in terms of the notion of delivering these things as a rented service rather than necessarily a purchased thing. These are ideas we're playing with at the moment. let me see. What maintenance do flow batteries require? They don't need any direct maintenance. The annual visit is really to make sure that there aren't creatures climbing into the air vents that keep it cool, and the fans that provide cooling for it. There are some other things we want to do just annually to them to make sure they're ticking along all right. Routine maintenance while they're working is nothing. When you completely discharge the flow battery, that is a maintenance cycle. It empties all the zinc off the plates, and then it's ready to go again. And that's what's called a strip cycle, strips all the zinc away. And it's something you have to work with in your applications with a flow battery, but it's also one of their strengths. How does zinc bromine compare to vanadium flow batteries? I know this might sound like a silly answer, but offhand, I'm not sure. My focus here is the technology on them more than the direct economics. So I have to check and get back to you on that. And the last thing, what's the Redflow battery? How's it affected by a repetitive 50% discharge and recharge? That's fine as long as it's the bottom 50%, not the top 50%, right? So there's no problem half filling it and emptying it again. But every 3 or 4 days, you want to completely empty each individual battery. The thing I want to emphasize about that is if you've got 10 of them or 100 of them or 1,000 of them, they don't all empty at once. The battery management system orchestrates them, so each of them takes its turn to do its maintenance cycle when it needs to, and it's quite invisible to people actually using the battery. And there you go.